Hi, I'm Kuba. Welcome back to Bielik Anatomy. Last time we optimized RMS norm and softmax using kernel fusion. Today we'll give our model a sense of time and we'll use RoPE as our time machine. Great, Scott! Take a look at this. Dog bites man and man bites dog, radically different meanings, right? But to a raw transformer, they're mathematically identical. Standard attention has no built-in notation of order. If you shuffle the tokens, the attention scores between them stay exactly the same. It has zero memory of order. So how do we fix it? Enter RoPE. Instead of just adding static position numbers, RoPE rotates our vectors. Let me show you the math. Let's start simple 2D. To rotate a vector q by an angle theta, we multiply it by this standard 2D rotation matrix. It's a basic linear transformation using sines and cosines. The vector changes its direction, but its length stays exactly the same. But Bielik's attention heads aren't 2D. They have 128 dimensions. So how do we rotate that? We generalize. We slice those 128 dimensions into 64 pairs and give each pair its own independent 2D rotation. Mathematically, it builds this massive block diagonal matrix. Every pair gets its own rotation angle. Here's our multidimensional clock. Every pair gets its own frequency, theta I. In the formula, d is our head dimension, 128 for Bielik, and I is a pair index. Notice that the base is 1 million. A massive base stretches the frequencies to handle long contexts. The final angle is just position m times theta I. This gives us a spectrum of frequencies from very fast rotations for low dimensions to extremely slow rotations for the high ones. When we calculate the attention score, we take the dot product of a rotated query at position m and a rotated key at position n. Because rotation matrices are orthogonal, when we multiply them, the math simplifies beautifully to r from n minus m. The absolute positions m and n completely disappear. The final attention score depends purely on the relative distance between the tokens. So where is RoPE in Bielik? Look at the decoder block. After the linear projection, we get three tensors. Notice the shapes. Q is 1536, but K and V are only 256. That's grouped query attention. We split this into 12 query heads, but only 2 K and value heads. Each head has a dimension of 128. RoPE is applied to Q and K only. V is never rotated. So how do we pair these 128 dimensions for our 2D rotations? We slice the 128 dimensions perfectly in half. We pair index 0 from the first half with index 64 from the second half. Index 1 pairs with 65, all the way to 63 and 127. Why does this split matter so much? Because it dictates exactly how we write our Triton kernel. Thanks to this layout, we don't have to jump around memory. We simply load the first 64 elements as a x first and the second 64 elements as a x second. Then we apply our rotation formula directly. Before we jump to Triton, we pre-compute a cache of sines and cosines for all needed angles. In our case, Bielik has a max context window of 8192. And we need to prepare this for all possible values of I. Notice this neat numerical trick here. Instead of calculating the base of the power of a fraction, which is expensive on the GPU, we compute this log scale in pure Python and just use torch.exp on the device. It's much faster. Then we just compute all the cosines and sines, and we are ready for the Triton. Let me walk through the actual Triton kernel line by line. The full signature has no output pointer. This kernel writes back in place. We launch the grid as n tokens, one program per token head. So the token IDX is just the flat index into the batch times seclen times num heads dimension. Program 0 handles the first token head, program 1 handles the second, and so on, in parallel. Then we calculate which batch we are in. We also fetch sequence ID to avoid expensive tensor reshaping and memory allocations back in Python, just to map position to heads. This is the addressing vector for the entire kernel. Block size is 64 for Bielik, equal to half dim, so the mask is all true and costs nothing. If half dim weren't a power of 2, block size would round up and the mask prevents out of bounds. Stride token is how many elements separate consecutive token head rows. Then we have two vector loads. X first gets elements from 0 to 63 and X second gets elements from 64 to 127. First, we calculate pos offset using our memory strides. And we load the position index for the appropriate batch and sequence, and then just jump to the right row of our cache table. Then we load pre-calculated 64 cosines and 64 sines. The 2D rotation matrix applied to 64 pairs simultaneously. 4 multiplies and 2 subtractions. That's the entire compute of this kernel. Everything else is memory access. Finally, we write back to the same addresses we read from. No separate output allocation. Now it's time for the benchmark, where we'll test our Triton kernel against the naive PyTorch implementation and compiled PyTorch across different head counts and sequence lengths. In both cases, Triton absolutely destroys the naive PyTorch. But look at this. For small sequence lengths and head counts, compiled PyTorch gets a massive bandwidth boost and beats our Triton RoPE. Initially I thought this was some profiling artifact, but I dived into the NCU profiler to see what the hardware is actually doing. And the truth is, torch.compile is slightly cheating the benchmark. Look at the Nsight Compute summary. The compiler didn't generate one single kernel. It launched a sequence of microkernels. To see why this matters, I ran the profiler with cache flashing disabled to exactly replicate our Python benchmark loop. And boom! We have a 99 L2 hit rate. Our tiny tensor gets locked in the GPU's L2 cache. We are measuring ultrafast SRAM, not VRAM. But in a production LLM, attention and MLPs constantly override this cache. This cleaner use is just a benchmark illusion. Our Triton kernel is honest. It reads straight from DRAM. Its slow start on the left is pure Python launch overhead, because our grid is too small to fill the GPU cores. But look at the right side. At real LLM context lengths, the illusion breaks. Both Triton and PyTorch compiled hit the exact same physical VRAM limit of around 350 GB per second. So that's RoPE. It's not a huge amount of code, but it has several sharp edges. The pairing scheme, the cache precomputation, and the fact that only Q and K get rotated. Today we also did our first real hardware profiling. We chased down a benchmark anomaly using Nsight Compute and proved why we should never blindly trust to the numbers without looking at the cache. Next episode we are going straight into flash attention. It's going to be a big one. Code is on GitHub. See you next time.